Okay, so let's look on energy associated with simple harmonic motion. And today we will look on a pendulum bob like this, and it will actually doing like this, the pendulum motion, but I will hold it like this and show you with this when I do like this, and then we will have to think of and see in front of us when it's actually doing like this. Okay, so we will draw pictures and see on the energy what's happening as it goes in this motion. And we will draw graphs to describe what's happening, and we will look on equations of the energy and see what's happening. And then finally I will show you one example. And as usual, if I'm drawing the pictures, the sketches too fast or the equations too fast, you can take a pause and start when you feel ready for it again. So, okay. Figure 1. So we have some roof or something where the string is attached to, and it goes down like this, and we have the bob here. So it looks like this. I have to hold it like this, and you don't see it when it is like this. Well, a little bit of it. Okay, so here it is at rest. So it has no energy. If we say that the potential energy at this height is 0, I can choose it to be has no energy there. Then on figure 2, still have the roof here. I'm lifting it up. So it is somewhere here. That is, it looks like this. And then I have to do a work. So I work on it and I'm giving it energy here. So a work is done. But I don't do any work for nothing. I have to gain something. And in this case, I'm gaining potential energy. And then it is there, I release it. I let it go. So it starts falling down to its lowest position. So let's look on figure 3. Then it has fallen a bit, something like this, maybe. So it has some velocity now, or some speed in the x direction, like this. So you see, if it's falling like this, and you look at it from the direction of my pen now, your eye is here, then it looks like it's only going in this direction, back and forth like this. And the potential energy is being converted to kinetic energy. We will see more close quite soon what's happening here. And then on figure 4, it is at its lowest position. So it's a vertical line like this. And it passes the center, or the equilibrium. The equilibrium because there is no forces works on it here, no resultant forces, because the gravity force is the same as the force from the string upwards, so they cancel each other out. So here the potential energy is equals to 0 as it was here. But it has a quite high speed now, at least it's higher than here. And it has the kinetic energy is at its maximum because it has loses all the potential energy. And then the last figure here, it is on the right side, something like this. And here the kinetic energy is equals to 0 because it's standing still. And the potential energy is at its maximum instead. And then it repeats itself. So it's like this in the beginning. I lift it up, give it energy, potential energy, and I let it go. And then it starts falling, reaches its lowest point where the potential energy is 0, but the kinetic energy as its maximum, because the velocity is at its maximum. The velocity makes it keeps going because of the momentum, so it reaches this highest point where the potential energy is at its maximum. And it's standing still, no velocity, no speed, so the kinetic energy is 0. And then it goes back again, and it keeps going like this. Now, how does it look if we would like to represent it with graphs? So let's draw the graphical representation. So on the y-axis, we have the energy, and on the x-axis, it's the time. And we have two energies, both potential energy and the kinetic energy. And let's look first on the potential energy. So on this point, we set a clock, so the time is 0 at this point. So the potential energy is at its maximum. And then I choose 4 squares later on. It's the time it takes for it to drop to its lowest position. Then the potential energy is 0. And it's a symmetry between these points. So 4 squares later, it will be on its top energy, potential energy again. And 4 squares later, it has gone back to the lowest potential energy, 0. So if I connect these, and it will be sine curves like this. I have to concentrate now, stay in focus. It looks like this. So we see this beautiful sine curve. If we instead now look on the kinetic energy starts at the bottom because it has no kinetic energy here. It's standing still. And then it gains energy, so it's going up. And when the potential energy is at its lowest, the kinetic energy is at its maximum. It's here. And then when the potential energy is at its maximum, the kinetic energy is at its lowest. That's here. And then it continues, goes like this. So it looks something like this. And you see these beautiful sine curves. We could understand that the kinetic energy has to be in this way because the velocity is a function of sine. I showed you that earlier on. The displacement is a function of sine, and when you derivative it, you get a sine or cosine function. They look similar. And if you take and square it and you multiply it with m and divide by 2, you get the kinetic energy, and it's still a function of sine. Therefore it looks this beautiful. And now we can see what's really happening here. Because you see, at the beginning it has potential energy and no kinetic energy. And then it loses potential energy and it wins kinetic energy. And at some point, some here in the between, they have the same potential energy and kinetic energy. But the potential energy is still decreasing, so the kinetic energy is increasing. And then kinetic energy as its max and potential energy as on its lowest. And then it starts to loses kinetic energy because it slows down. So it goes down, but it gains potential energy instead. They meet somewhere here in between. And then you get more and more potential energy and less kinetic energy. And then you have it in this position. Maximum potential again and lowest kinetic at that point. And then it starts all over again. So you can see how the energy changes between each other. And there is no loss in energy. The energy is conserved. Okay, let's look at this on equations. So, first of all, I have to remind you that the velocity on this bob depends on the distance away from the center. not on the center according to heights, but in x direction, in this direction, because it goes away in this direction and it goes back and it goes in this direction. So you just look at it from this perspective. Then the velocity depends on the angular frequency, the frequency, and on the displacement. Well, on the amplitude, but that's a constant, minus the displacement, and you square it, and you take the square root of it. You could look on the velocity, how it changes with its time, if you have the sine function, or how it changes with the displacement. So now we can see that the highest velocity, the greatest velocity, is when x is 0. And x is the displacement from the center. So when x is 0, it has its highest velocity. When x is equals to x0, the amplitude, it's over here. Then x0 squared minus x0 squared is 0. Therefore, the velocity is 0 over here. And it's also 0 here, because you have a negative value for the displacement here. It doesn't matter. When you square it, it becomes positive, and then you subtract anyway, so it's still 0. Now, I would like to look on the energy. And the kinetic energy is like always this formula. But now the velocity, we will rewrite it in this way. Can you do it? You can take a pause now and try to exchange or substitute this v to this and see what we get. Okay, we'll start with an m. And then we multiply with the velocity and we square it. So we square this expression. Then we have to square the omega, the angular frequency. And then we have to square this, but then we take away the square root. So we have x0 squared, the amplitude, minus x squared, and a brackets around it, and we divide with 2. So we see how the kinetic energy depends on the distance away from the displacement. The mass is a constant, the frequency is a constant. You see, this has to be a constant, because if I lift it up and drop it, it will always have the same frequency. No matter how many times I lift it up and drop it, it always have the same frequency. If I don't change the distance, the amplitude, then I change it, but then that's another constant, and I still will have the same frequency for the same amplitude. Okay, so this is the kinetic energy. What is the maximum kinetic energy? K energy max. Well, you have the maximum energy when it passes the center. Then the x is 0. So I just take away this term, and we get m omega squared x0 squared divided with 2. This is the maximum energy. Now, let's look on the potential energy. The potential energy. Well, the potential energy is the total energy minus the kinetic energy. But what is the total energy? Well, let me show you that here. It's very beautiful when you see it here. The total energy is the sum of the potential energy and the kinetic energy. And if we start as the time is 0, the sum of the energy is 0 plus the potential energy. That is on this point. The sum of the energy here is this distance plus this distance. And then I'm coming to this distance. Well, it should have been drawn a little bit better here. They should have meet each other here. So I take this distance and twice it, and then I reach this point. The sum of the energy at this time is 0 plus this value. Well, that is that value. The sum of the energy here is this value times this value. It's this height because of the kinetic energy and this height again because of the potential energy. When you add them together, you reach this height. 0 plus this height is this. And you can even see, if you look here at this time, you have a small value here for the kinetic energy and a high value, this value, for the potential energy. When you take this value and you add this small value, you will reach this point. Here, the sum of the kinetic energy plus the potential energy is here. So you see, when we draw a line through these points, we have a horizontal line. That means that the total energy is a constant. It doesn't change. So, therefore, if I would like to calculate potential energy, the total energy is the same as the maximum kinetic energy or the maximum potential energy, but I don't know the potential energy so far. So, the potential energy is the total energy, that is the maximum kinetic energy, minus the kinetic energy. So I will not do it. You can do it as a good practice. You take this value and you subtract it with this value. It's more algebra than physics. So you have to multiply these two factors with this term and these two with this. And then you subtract with this, so this x0 squared will cancel each other out, and then minus, so you will add with this value and this. Do it for yourself. You will get m omega squared x squared divided with 2. So the kinetic energy has to do with the x0 squared minus x, and the potential energy with just the x value. So the higher value on x, the higher potential. The higher negative value on x, the higher potential, because when you square a negative value, it's still a positive value. Here, it's some kind of inverse function, because when you get higher values in x, you do a subtraction and you got a lower kinetic energy. Oh, I'm talking so much. Let's look on an exercises on this. So here you have it. So write this down in your own notebook and try to solve this first equation. No, this first exercise. Calculate A, the frequency. So, a pendulum bob of mass 20 gram. That's almost exactly what I have here. It's 20 gram. Swings with amplitude 8 centimeters. That's 8 centimeters in the x direction. 8 centimeters to the other direction as well. And the time period is 0.8 seconds. Calculate the frequency. Do you remember how to do that? If you do, take a pause now and do it. Well, the frequency is the inverse function to the time period. You calculate it as like this. So it's 1 divided with 0.8 per seconds. And when you calculate it on your calculator, you will get 1.25 per seconds or hertz. So in 1 second, it does a little bit more than one full, circle or period. Okay. Next question. Calculate the angular frequency. The angular frequency. Look in your notes from older lessons, or look on your physics booklet and see if you can find a formula about it. the angular frequency is 2 pi multiplied by f or divided by capital T, the time period. So in this case, it's 2 times pi times 1.25 hertz. If I would like to calculate it, and I would like to, I use my calculator. So 2 times pi times 1.25. And I have to round it off now. It's 7.85, not hertz. And of course, I don't have any eraser here now. So I'm really sorry for this. This is not beautiful at all. I should have been very angry with you if you would do the same thing, because this is radius per seconds. 7.85 radius per seconds. Okay, calculate the maximum kinetic energy. So take your time and do it. You might need to look on the other side to remember the formula, or you can look on your booklet and see if you can find it. So the maximum kinetic energy is equals to m omega squared times x0 squared divided by 2. When x is 0, it passes through the center, but you need the amplitude anyway, because if the amplitude is higher, it will gain more speed before it reaches it. So the speed and the kinetic energy will be higher. So with our numbers, and I have to convert now to kilogram and to meter if I want it in joule. So the masses is 0.020 kilogram times, and then this is a rounded off number. I will not use it because then I can at least not round off the numbers, so I use this expression, 2 pi times 1.25. This is omega, and then I square it, times x0, the amplitude in meters, 0.08, and I square it, and I divide with 2. And this is the maximum kinetic energy. Let's see what it is. So 0.02 times brackets 2 pi times 1.25 end of brackets, and I square it, jumps down again, times 0.08, and I square it, and I press enter, and I divide by 2, and I got 0.00395 and 5 with 3 significant figures joule. D, the maximum potential energy. Can you find it? Well, that's an easy part. The potential energy and the maximum value is the same as the kinetic maximum energy. So it's 0.00395. It's not just happen at the same time, it's a moment later. When the kinetic energy is 0, then the maximum potential energy has the same value as the maximum kinetic energy. Okay. E. The kinetic energy when the displacement is 2 centimeters. Can you calculate it? Try to. The formula is like this. The kinetic energy is equals to m omega square x0 squared minus x squared. Brackets around it, and you divide it with 2. That equals 2. Now, let's put in all we know. 0.02 times 2 pi 1.25. I square it. I take 0.08 and square it minus 0.02. That is 2 centimeters. And I divide it with 2. I need the brackets around here. And I need my calculator to calculate this. So I start here inside the brackets. I think that's the most easy way. 0.08 squared minus 0.02 squared is equals 2. Then I multiply with the brackets, and then I take 2 pi and I multiply it with 1.25 end of brackets, and I have to square it, and then I get this number. And then I multiply with the mass 0.02 and I divide with 2. And then I will have in joule 0.037 joule. Okay, and finally, the last question. The potential energy when the displacement is 2 centimeter. Can you do it? Then you start trying to do it. Okay, so I will show you. You could use the formula for the potential energy now, of course. But we have already calculated the maximum energy and the kinetic energy at the same time and at the same location. So we know if we take the maximum energy and take away the kinetic energy, that has to be the potential energy. So the potential energy is equals to 0.00395 joule minus 0.0037 joule. So what's not is the kinetic energy, has to be the potential energy up to the total and maximum energy. So 0.00395, I can go up and pick it up with the arrow like this. Here I have it, and I press enter, and then I take minus and I jump up one step with the arrow and I press enter. So then I have all the digits, so I don't round off anything now. And then I press enter, and I got, well, it's a small number, 2.47 with 3 significant figures times 10 to the power of -4 joule. Oh boy, this is energy in graphs and equations. Thank you for today.